tired.
You're still young.
Yeah.
That's what I keep trying to tell myself. But you know what? It's getting less and less true.
No, good go.
They go checking my email.
Yes, the pants on fire is found.
As you can tell from the clock here, they've already burned one.
My goal in life, you'll have to negotiate with just never have a pants on.
Red tea.
We have these
What's the reading rule?
Because when we're over the top, verification requirements and stuff.
Pause it right there.
We spend half our time talking about like a requirement. Time to close.
It's all about process. You gotta have good process. George?
It's not like the process.
It's like in professional sports, right? You
I'll ask Matt.
Yeah, if I can.
Again, would be
Yeah, that
Thing about these possibles now, professional science.
oh, actually, that's cool because it's a location.
Budget.
What we like to hear.
That's the problem.
Oh, that's, I know that is.
Like,
How good is this call?
See, I'm not going to end up responding.
it's 2 minutes fast.
Otherwise, I'm the person.
that's not correct. So let's talk to the next guys here.
This one teach me to take on actual linearization. Oh, yeah.
Yes, of course.
Yeah. Because the linearization I get,
We're assuming 5 minutes.
questions, right? I get no machine. When they give you they never use so like really
I'm just saying, I'm wondering, in engineering, but I'm wondering if they have very similar.
because he's very level computers on it has to be like device changes color.
So you're in that corner, I said, you mean the big one is coming in, you're not going to be able to tell. That is shocking. So we won't know.
So they're just like, the lights turn on, or they check
This is 15%.
Yes, now it can and then some of them, yeah. Whatever it is. Yeah.
How you can fit it. It's just a big deal.
So we're last week, so I'll try to data point doesn't use smart because I was young. They're recording to that's the intelligence objects,
And it has people from
so science.
just a bunch of them talk about different inflection techniques. Because they have these simulations.
All right, we're at 1:20, so we're going to get started. Hello, everybody. Welcome to session 6A. Is this on? Now it's on, I think. All right, so my name is John Devis. I'm the chair of this session. We have a great moderator. There you go. And we have Florian Kerber for our first talk of the session.
Okay, thank you very much. You can hear me okay? Good. So, first of all, thanks to the organizers for inviting me. I think it's a really great workshop. I'm learning a lot. And thanks everybody for coming back. And I know I sympathize with your body's natural tendency to ask for a nap now, but I will try to counteract this the best way possible. Just a few facts about ESO, the European Southern Observatory. So we have been founded with the aim of providing access to the southern sky, in particular the galactic center. You know that the Nobel Prize 2020 was a shared one. So we have achieved that goal. We are fairly similar in size actually to the STSCI, but we are split between the center in Europe and the one in Chile. And then we have 3 major telescope sites, and you will notice that we are not very imaginative with our names of the telescopes. They all end up being very large or new technology or extremely large telescopes. We have tried to do better, but not very successfully. This is just a reminder of what we are really doing. We are not doing science on our own, really. We are not a research institute as such, but we are a service provider. We build and we operate the telescopes and the instruments for the member states and the community. And this, of course, is also what we are doing. This is why I'm here as well. Now, just to give you an idea of how that looks like, and that, I've been working for what was called at the time the Space Telescope European Coordinating Facilities. I've been here many times. This is one of my favorite pictures where you see this is the Pacific coast of Chile. There's the cold Humboldt stream coming up from the Antarctic. We have always a cloud deck, which is basically trapped underneath an inversion layer, and that means we get many, 85% of the time, clear nights at our observatory. The Atacama is one of the driest places on Earth. We have a median of about 2.5 millimeters. Atmosphere is very stable, and all in all, this is a remote and pristine site, and actually our host country, Chile, is helping us a lot to keep it that way. We have a very large and active community, so that means if we can improve our calibration, we have many people who benefit and a lot of science that benefits from this. Now, this is my take. I think Chris used the term astro-sociology or something like that. That is my take on it. I'm making the distinction between, the observers in a traditional sense and what the observatory is doing. And I'd like to focus, I think you said passive-aggressive or something. We have this sort of passive role as an observer, traditionally, right? And that is something we can no longer afford here, because in the end, what we have is an experiment, and I think Daniel and also Joe used the term apparatus. So you absolutely need to have this active role like in experimental physics. Then, of course, the atmosphere traditionally is a nuisance, but what can you do about it? And that is also completely different now, because we're really trying to understand and counteract the negative effects of the atmosphere the best we can. And I think this is also an important thing, that since the astronomers are observing across many different wavelength bands, using different facilities, they are no longer really in a position to have all the expertise that might be needed, and hence the observatory needs to simply take care of that. And I think we all have the calibration plans now. 5% is sort of the generic number. And we have the option to actually have additional time for additional calibrations to be requested by the observers, by the astronomers, but it's a rare thing, and I would actually like to congratulate the people who have done this here successfully, bringing it down further. It can be done, evidently, but what we notice in terms of sociology is that not that many people actually are doing this. They're quite happy to take the 5%. That is changing with the science cases that we have seen here. Now, what are we doing with the data that we have from monitoring our atmosphere? First of all, we make real-time decisions at the telescope based on the conditions in the atmosphere. Our observers can tell us whether they want to have, lunar phase, of course, is very evident, but you can ask for very dry conditions. You can ask for certain specific conditions in terms of turbulence. In the future, ozone may be a relevant one. So we make these real-time decisions at the observatory what to observe if it is in service mode. Then, of course, forecasting, the better we can do that, that helps us in the scheduling. And what is also quite important now is the calibration that we can do afterwards. And I will have a few examples for you. Okay, this is one here. Of course, very relevant for flux calibration. This is about sky transparency. We use the infrared sky brightness temperature that is measured by one of our radiometers. We're just looking up, or we point it somewhere. And we have actually a quantitative definition for these 4 levels, photometric through thick. And you see this is a fairly small variation. This is about 2 degrees C or Kelvin. That's something you will not be able to see with the naked eye. I mean, the clouds we have usually is very thin cirrus anyway, and these are very small variations, but we can reliably detect them. And then, as you see here, it will actually move into the clear and is no longer considered photometric. The other one is dealing with the water vapor, the telluric absorption in our atmosphere. And as Matt will have to say a lot more about it, but what is, I think, very impressive and also very important for us is that if we take the data from our radiometers, that is the temperature and humidity profiles that we get up to an altitude of about 10, maybe 12 kilometers. Same time and same location, and ideally same line of sight. We are providing this now. Then you can get a very, very impressive correction, and Alain is going to tell you much more about it. If you only use one of the global models, which are, of course, averaged in time and in space, it works a lot less good. Okay, then what is needed in terms of accurate flux calibration? I think we have all seen this, and I would very much argue to the same end. We need a proper reference. We want to be able to link this to a laboratory standard. Of course, top of the atmosphere, and I think that's also very important. We need to have the calibration's reference data. Yeah, we need to have the pedigree, know where it's coming from, and so on. What we are very much working on is to have a real-time, many parameters characterization of the atmosphere. You need to have a comprehensive understanding of what your light is going through. Most of this can be based on models when you want to correct it. And then I just wanted to highlight a bit about the future. We are building these extremely large telescopes, which will offer D⁴ performance for point sources. And that will only happen if we are able to achieve something that is relatively close to diffraction-limited performance. Otherwise, you just have everything smeared out, and these telescopes will not be delivering anything near what we can. So we will have the laser guide starts, we have the adaptive optics, and then, of course, we need to reconstruct the PSF. And this is just an example. It's a relatively old picture, but for reference, you have a tennis court or a basketball court, whatever your preference is. And this here is one of our 8-meter telescopes, the VLT, and here on the right-hand side, we have the ELT. And in terms of physics, it's very clear. I mean, you want to go ahead, you want to have this large aperture, not only for the light collecting ability, but very much for its ability to then, discern fine detail. On the technical side, well, here are just some numbers. I mean, in the end, if you would take 1 hour on the ELT, it would take on the order of 42 nights on one of the 8 meters. So this is really a huge jump, provided you are diffraction limited to at least a certain extent. Problem, of course, is, Technically, you can no longer make this a monolith. You have to segment, and you have to be able to phase all of these segments, in our case about 800, to the same kind of fidelity that you really get an optical surface that is good to a few tenths of nanometers. And as I said before, if you want to be able to observe diffraction limited, then you absolutely need to have the optics working. This is how it works. You take a certain part of the incoming light with a beam splitter, you analyze the wavefront, you basically invert the matrix, and with that you drive a deformable mirror that is then correcting. That would be upper end here, a seeing disk, and down there the area disk from the diffraction limited, all by AO. That we have mastered at this point for standard observations with a very large telescope, that's routine. But we also need to have this working to a much higher degree, because the whole telescope, given the big diameter, is much more vulnerable to the effects of the atmosphere. This is an example of the kind of instruments we are building. This is about 7 meters tall, comes in at about 25 tons of weight, so this is really a truckload. It will be operating behind a multi-conjugate adaptive optics system. And what is really important, they want to do quantitative science, really also astrometry and proper motion work. So we need to have that kind of performance. Has passed its final design review. And if it works, then this is just a comparison between HST with 3, JW and NIRCam, and then ELT. So here, the big diameter really makes a huge difference in performance. You will be able to operate at much higher spatial resolution, and of course the calibration that comes with it. Now, we are trying with this campaign to basically put ourselves into the future. We are trying to test what it actually takes to be able to work and operate the ELT and to understand the atmosphere and correct for its negative effects. And I'm not asking you to read all of this. The main point is that we are trying to validate our existing capabilities. We already have quite a few monitoring systems for the atmosphere, and we want to make sure that we properly reference this. And the key for this is really to use the best radio sound, which is flown on a balloon. Come back to that in a minute, because this is the gold standard that the people in the meteorological and climate research are using. Then we are looking into capabilities that might be very useful for the future, but we don't really have them yet, or they are at some experimental level. We are certainly interested in making a good comparison between the measurements and the models that we have, to validate the current but also maybe future options for the atmospheric models. And in the end, all of this, as I said, it will put us, for a very limited period of time, it will put us into the future. The capabilities we might have, let's say 5 years from now in an operational sense. So we really want to inform how we operate the telescope once it is operational. This is just to demonstrate that we have some requirements flow down that we did. So we are going for a campaign mode. We will use the best standards. We will apply the best calibration step. Koruman is an upper air atmospheric research part. And we are building on a recent campaign that was conducted by the World Meteorological Organization. This is just an aerial view. This is our current observatory on Cerro Paranal. This is the construction site on Cerro Aramazones. And down in the valley, we have another observatory that's going to be built. That's the Cherenkov telescope array. I'll come back to that later. And just for your curiosity, this volcano in the background is at a distance of about 190 kilometers. From the aircraft, that's not a problem to see, but in fact, we can see it like 80% of the time from the platform. So we have a totally horizontal line of sight. It would not be visible if it wouldn't be that tall itself, otherwise it would be gone because of Earth curvature. But we really have this enormously clear atmosphere, sort of ideal conditions for ground-based, let's say. Good. So what are we trying to do? We are trying to combine in situ and remote sensing measurements to sample this 20-odd kilometer slab of the atmosphere above our sites. We will launch the radiosondes from about 2300, maybe an alternative site 2500. We will have these fixed sensors at 2 levels. I need to keep you in mind that we are not only in 2D now for the, between the mountains, but we really are taking the 3rd dimension here. We will have drones equipped with sensors. They can probably go up to about 6 kilometers. We will do this 2 times to cover the seasons, 10 days each, 2 launches per night, 1 during daytime, so a total of about 60 launches. And we will have all kinds of additional equipment to actually make the kind of comparison that we need. And we also plan to carefully coordinate some of these things with satellite overpass, because there is a lot of information to be extracted from that as well. This is just for illustration. If you are not familiar with a radiosonde balloon, this is simply, well, a balloon. You fill it with helium or hydrogen, so it will actually go up to altitude 20, 30, maybe a bit more kilometers. And in this particular case, this was part of the campaign that they did by the WMO at Lindenberg, where that's close to Berlin. And in this case, they are flying on a bamboo rig. They are flying 10 of these radiosondes in parallel for intercomparison. The radiosonde itself is a little box, a few centimeters aside. It will measure for you the temperature, the humidity. You will get the GPS signal for the wind, things like that. So you get a beautiful profile that's along the trajectory of the radiosonde. It goes up at about 5 meters per second. And in our case, in the end, they all go to Argentina because Chile is so small and the jet stream will always take them back. No, stuck. Okay, so this is a different view of it. We will have meteor stations and LiDARs and radiometers here on these sites. These are the mountaintops. This is the area down in the valley that will be for a CTA. This shaded area basically shows you the typical trajectory that one of the radiosondes will be taking. Locally, close to the ground, we usually have the wind coming from the north, but if you go up a little higher, it will always go to the east. And we will, that way, if we launch fairly far out west, we will be able to sample pretty much all of the area that we need to have. And we're not doing this alone. We have partners. You have seen Joe Rice just previously. Susanna is here anyway. John is here in the background as well. And we have this NIST project, which will be aiming to make that link to the laboratory standard. I'm very happy to have that on Paranal in Chile. They will also bring for the campaign an eye-safe LiDAR, backscatter LiDAR, so for the aerosols. And this is the chain. Power is not in here because this is a bit of an outdated diagram, but you heard about it. So we will really have the full chain from the laboratory going all the way up to the sky. And I think that's really something that will make a difference here. Then we have CTA. What is important is that they're looking at the air showers. So the cosmic radiation coming in, and then you have the muons and everything else. You have the blue light. For them, the atmosphere is in fact the detector. So if they don't understand it, they don't understand the detector, and they will be massively compromised. So they need to invest quite a bit. They are part of this campaign. Specifically, they will also bring a LiDAR. We have an elastic channel and then 2 Raman channels. That has been operated before on La Palma. I can show some results here. On the left-hand side, you see the aerosol backscattering coefficient. This here on the right-hand side is the water vapor. And this will be a time series. So you see a seasonal variation in the aerosols, and then you see some specific events, like if there's a volcanic eruption, of course, you get more aerosols. So this is the kind of information that we will also then have in real time to tell us about the state of the atmosphere. Good. Additional partners we have in Chile. We have very good relations with some of the universities. They will bring drones that fly for us. The big advantage of the drone is, of course, you can launch from wherever you want. You can put it to a certain altitude. You can go up and down, things like that. So they will be doing something that is quite similar to the radiosonde. We may actually try to follow some of the radiosondes directly to get a second profile a few minutes later. We will have a tethered balloon going up to 500 meters. Then we have equivalent sensors at different altitudes, so we have different, let's say, echelons in the atmosphere. Gruan, as I said, is this upper air network that has a special calibration step. You get the data product out of it, so this is really the best you can do in terms of analyzing radiosonde data. And then we have already support from the Swiss and the German weather services. We get some training, we get expertise. So we really are covering, somebody was asking about the WMO previously, so we are really combining the expertise for that. This is how it will look like. I just highlighted here the area where we have the VLTs. Close to here, NIST is building the facility for the NIST stars. And at the moment, let me just very briefly focus on the radiosonde itself. So we will be launching most of the time down here from what we call the Residencia. So this is our hotel. If somebody has seen the movie Quantum Solace, James Bond, it was blown up. It was the headquarters of the bad guys. Fortunately, the damage was very limited. So this is one of the launch sites that we have. And the second one we are interested in is for some special things where we really want to sample the exact same volume of air that our line of sight of the VLT observations go through. So there we will try to get directly into this with the drones and with the radiosonde. So that would be a second launch site very close to the telescope. In total, we'll have many things. We have a seeing monitor, we have the tethered balloon, we have the radiometers. We need to bring all of this together. So it's getting fairly complex, but yeah, I mean, we think it's worth it. Now, where we are with this, funding is in place on the ESO side, also from the partners. We are iterating the plan. We are really deciding what is worth doing, how experimental is it worth it? We'll have a science advisory body in place that helps us with that selection early next year. We will start the procurement very close after that. Then, of course, we need to request technical time at our own facilities to make sure that we have the right kind of observations that we can then accompany. What we also still really need to work on is a detailed plan for the data analysis and the science exploitation, because we need to bring together these different disciplines. And I'm giving some very precise dates for the campaigns. This is simply because this is the full moon date. And since we will be operating a LiDAR and other lasers, we will be contaminating the sky for other observations. So it will be done close to the full moon. One campaign, October or maybe November 25, and then the next one in spring, Northern Hemisphere 2026. And then, of course, we will need a bit of time to actually analyze this, but it can be completed, all of it, definitely in time for the ELT start of operations. And then, of course, I think since this is an invited talk, I probably give you a bit of an idea what the future might look like. Some of that, I think, is fairly clear. I mean, we will need to have a real-time, multi-parameter characterization of the atmosphere in 3D. This is just a given. This can only be achieved by combining remote sensing and in situ measurements. The in situ will not be any balloons, because we are not flying 3 balloons per day. That's just operationally totally impossible. But drones can pretty much do the same thing to a given altitude, of course. And there are already systems that are completely automated. So they have a launch pad, they go up, they come down, get recharged, go up. So they can basically operate all night. What is really key is that with this kind of data that we will be acquiring locally, the term by the meteorologist is to assimilate. So you can put these data that you have measured locally into the global forecast, which means you can improve your local forecast. And that brings us to this airport model, where you really want to have not just a single mountain, but you have an area, like an airport, where you want to have your high precision, high fidelity, short-term, maybe a bit longer, but mostly short-term forecast. What I think we also really want to have, and I'm very happy, I had a conversation with Justin about the altar. Great talk by Peter for the landlord. I think this is what we want to have, right? We want to have that reference above the atmosphere all the way. As I said before, calibration reference data certainly based on SI. And for us, what will be key is that we need to bring all of this together. I mean, there's many pieces of the puzzle, and we need to be able, we have an excellent site, we can monitor the atmosphere so we can decide which observations to do when under the right conditions, including the forecasting. And then we need to be able to model the atmosphere to counter the negative effects, whether it's telluric correction or the reconstruction of the PSF. But all of this needs to come together. Let me just close with this picture of two mountains. How do you do that? If you want to take a picture of two mountains, you're standing on one of them, and this illustrates very nicely the effect of the atmosphere. This is the shadow of Paranal cast onto the atmosphere below us. This is the construction site. And just on a very personal note, I'd like to finish by just saying thank you to Michael Rosa. He passed away a few months ago. Without him, I would not be standing here. He was a great teacher, great person. So I'd like to have this here as a little memory of his. Thank you very much, and I'll be taking questions.
Okay, questions? Yes.
It's not a question. I want to congratulate you for quantifying when it's photometric, when it's clear, when et cetera. That's in itself is a big step forward. I haven't seen that before.
Thank you very much. We have actually worked more than 10 years on this, and we have at least failed twice in the process because we thought we had a solution, but it turned out it was too dependent on the hardware. What we now have, we think, is independent of the hardware.
Great. Yes.
How many parameters do you think are sufficient to characterize the variable components of atmospheric transmission?
I don't have a number for you, but I think what we absolutely want to have is the aerosol optical depth. We are measuring the water vapor in parallel for sure. In the UV, we plan to do the ozone because we will have an instrument that is dedicated to 300 to 400 nanometers on the VLT, everything UV optimized. These are the things that we really have on our list, but I don't think this is complete. But these are the things that we certainly know we can deal with.
Any other questions? Okay, any online questions? All right. Well, let's thank Florian again.
Thank you. And just as a final remark, if somebody is interested in being part of that campaign, talk to me.
Great, thank you. All right, so we have for our next speaker, Simone Garapa. Simone Garapa will be our next talk. I'm just gonna get set up.
Can you hear me fine? Okay. I can't see my file here.
You might have to go up one level. Still on the desktop.
Someone knows where the other files are stored?
Probably on the desktop.
I can probably
Would be, yeah.
Okay, thank you.
You know how to get it from there, because that's when I start.
Okay. I hope that center full screen will work. Okay.
Thank you. So, my name is Simone Garrappa. I'm a postdoc at the Weizmann Institute of Science in Israel, and I want to thank the organizers for the opportunity of presenting this work. I'm pretty new in the business of optical calibration. I also come from higher energies, and I am giving this talk on behalf of Eran Ofek and the whole LUX collaboration. LUX is a different instrument compared to those that we saw in these days. It's actually an array of small optical telescopes, and I will tell you more about it in a few minutes. But first, I want to start with how do we approach the problem of the absolute calibration in our case. We know that there are many efforts going on in breaking the 1% level of precision in the absolute calibration, but this is very difficult, and this is due to instrumental factors and the variable atmospheric transmission mainly. Here, just as an illustration, I'm showing like what would be the effect of just mismatching your passband by a little when you have like a different kind of stars. And for some spectra, you will have like very little effects, but in other cases, this might be more tragic. And so the real-time monitoring of the atmosphere has been proposed, has been successfully applied, as we saw in the case, for example, of the forward calibration yesterday. However, this might be not enough, and not enough, especially to catch some short-time variations in the real passband. So the ideal case would be to have the system and the atmosphere transmission infer directly from data from the observations on an image-by-image case. And this will be very difficult if we only have a limited sample of calibrators, so we need a much larger one. And so how did we address the problem? So we got some help from the recent large set of Gaia X-peak spectra, and we asked ourselves, can we do this image by image absolute calibration, so try to infer the transmission of each image instead of having like a lower sample of very good calibrators. What if we have many of them but with lower quality? And the general formulation of the problem is not so complicated, but it's very complicated to actually solve it. We saw it yesterday, some beautiful talk about it. And since this is, in general, this approach will be computationally unstable and difficult to address, we approach it with some kind of regularization. So defining a model of the transmission, a sample of calibrators that we get from this large set of Gaia X-peak spectra, no more than 30 million spectra. And the other ingredients that we need is only the instrumental photometry that we measure from aperture photometry or PSF photometry from the images. So what will be the model for the transmission is the classic representation, a lot of independent components. The first one is we need the instrumental that has the optical element transmission, and what we define the detector transmission is basically the quantum efficiency of the camera and the filter whenever is there. And for the atmospheric, we include a series of components like scatter, aerosol scatter, ozone absorption, water vapor absorption, and uniform mixture of gas to include all the other components that are not included in the first ones. And the general form of these components is almost always the same, and we get the parameterizations from the smart model. And the final term that we add here, some kind of perturbations in order to correct from some effects that are not really included in the model. Generally, you have a basis of polynomial corrections to the model that you can fit eventually. So how do we optimize this model? Basically, we do it with synthetic photometry. Basically, we want to match the expected count rate that we have in our detector for each source that we select with the one that we measure actually the image. And we do this by minimizing these residuals, so transforming, bringing everything in magnitude space, and we add a term that actually helps us to correct for. We call them field corrections. Basically, everything you can have once you extract your first instrumental photometry from the images. You have residuals from far field correction. You have non-uniformities in your detector, and so everything like this can be corrected with this. Also, like usually use basis of polynomial basis. Legendre polynomials, Chebyshev polynomials, you name them. So, time to talk about LUX. LUX is an array of small optical telescopes that is designed on the concept of cost efficiency. So instead of building one single instrument that is very large, we build an array of small off-the-shelf optical telescopes, and in the end, we'll have the same performance of a large telescope. The node is currently consists of 32 telescopes. When the node will be completed, we'll have a total of 72 telescopes, and these are 11 inches f2.2 Celestron Rasa telescope, and each telescope has a field of view of 7.4 square degrees. And we have two main data products from LUX. We have a very high cadence. A single image is taken at 20-second exposure, and then every 20 images we define a visit, we coadd them, and then we have the so-called coadd images or visit images. So since the field of view is pretty large, we divide before any kind of calibration, starting from the raw images, the image in 24 subparts that are slightly overlapping, and these are squared parts of 0.5 degrees per side. And in each one of these sub-images, on the median number of Gaia calibrators that we have is about 130. It's a good number. Of course, this depends on the field, but this is the median value that you get. So let's start to see like how do we tackle the problem with the on LUX data. We don't have filters on LUX. LUX is intended as a transient discovery machine. So we have a broadband to try to infer from data. You can see here in green and orange the single optical elements, and the black points are the laboratory measured points for the quantum efficiency, and then we conveniently try to model this quantum efficiency with a skewed Gaussian with some kind of perturbation, and we want to let some of these parameters free to infer from data little differences that we might have across the sensor, because usually these measurements they're taken on axis, and also get some freedom for the transmission to vary. And okay, what about the atmospheric transmission? I listed before the components. You can see here the different transmission models. But what is more interesting is the effect on our broadband that each one of the parameters has. So at some point we needed to make a selection, because fitting all together these parameters is not really ideal, at least in the case of LUX data. And so basically you can see here the pressure, atmospheric pressure, the length of the ozone column, and the aerosol index alpha are contributing very little on the variation of the 0 point if we fix all the other parameters and let this single parameter each time to vary. So we fix like some kind of limit at 5 millimagnitude of the contribution of these parameters, and then in the end we have that we let these three parameters in our fit, And the temperatures, we actually measure it on site, although the contribution is very little, because only the uniform distribution of gases is depending on it. And then we are left with fitting the aerosol optical depth and the amount of water. So let's go on the results. We have a total of 14 free parameters that we fit for each image to infer the transmission model. We have 2 from the instrumental model transmission, 2 from the atmospheric, and 10 from this field correction I was telling you about. And you can see that the residuals for the single 20-second image are pretty good. We have 0.5% sigma in the distribution of the overall residuals. Here you can see the set of all the transmissions of the single sub-images in the main image. And this in the center, green and red, are the residuals versus the instrumental position of the sensor. You can see we don't have any trends after these corrections all over the sensor. And also the residuals versus the Gaia color, they don't show like significant correlations. And here we have the overall residuals versus the magnitude of the calibrators that we are using. And when we go on the co-added images, so the results of co-adding 20 images together from the same visit, we gain something on the scatter of the residuals. This is not like a factor square root of n, more like a factor 2 in total. And you can see here the residuals in the previous case. Then we wanted to kind of try to estimate the error on the 0 points that we have while doing this calibration image by image. In order to do that, we used a non-parametric bootstrap approach. So basically, we have our image with all the calibrators, and we create a bootstrap representation of this, but randomly sampling with repetition these calibrators every time. So then we calculate the 0 point every time for a grid of positions image, and then the median error. Basically here I plot the error for each position in this grid of the 0 point that we get at the end of the whole bootstrap procedure. And so the median error on the 0 point in the case of the single exposure is around 5 millimag, and for the co-add images is around 3 millimag. And lastly, I want to show you what is the stability over time of our approach. Basically, in this case, I'm showing here, I consider 8 nights of observations. For each night, we observe this field for a single visit. So we have 20 images per night, per 8 nights. So for the blue points, they are for the single exposures. We see that the scatter on the bright end before we start being saturated in our system is around 7-8 millimag. And we gain something with the co-add images where we have a scatter around 3-4 millimag. But you see here is a bit larger because we only have 8 images in this case. And so this brings me to my summary. So we wanted to approach this complicated example of absolutely calibrated last data. Since we have so much multiplicity in our system, it's not about just characterizing single detector, a single optical scheme, and a single set of results. We wanted to try to derive the transmission, on an image by image base. And the key element for this approach is to have this very large set of Gaia calibrators. The results that we have right now on last data show that we can achieve like a good accuracy on the 0 point and also a good temporal stability. The main limitation, of course, we need a large field of view, so it's not for all systems to get that, but even by just taking the sub-images, we have enough field of view to have a large number of calibrators of diverse magnitudes and colors almost every time. And this image-by-image calibration also can be expensive, but has a large margin for speed optimization. And the paper will be out very soon, so stay tuned, and thank you very much for your attention.
Okay, thank you very much. Any questions? Yes.
So this is interesting. I was wondering about your skewed Gaussian, which if you don't do that, I assume nothing is constrained because
we have
too many degeneracies. But I'm wondering, do you force the blue end or something to be in a particular location?
So we start from the laboratory measurement with the model, okay? What helps really with using this skewed Gaussian model is to get rid of the color terms, the color dependency. Because in different parts of the detector, we have that the effective transmission is centered on each one of the sides, okay? We don't get, we don't see problems of like diverging into other solutions, like other solutions that give you the same integral flux, but with totally a different transmission, but only because I only free the center of this skewed Gaussian and I modulate the amplitude.
Okay, that's what I was.
So if I free everything, it's
the other thing is from night to night. Is that fixed to be a common parameter, or is that floating from day to day? Because I don't think the instrument should change that rapidly.
So what I can tell you that being in a desert, we see large variations of the transmission.
But the instrument part, I don't think should change.
I can which one? No, the instrument part. No, the instrument part is very similar for close by nights. Now we just started operations a few months ago. Almost continuously. So in the longer term, I'd like to see like the more seasonal variations or like degrading of the same instrument for very longer time scales. But on a night-by-night basis, what is changing a lot is mostly because of the atmosphere, and especially the aerosol component is for us is very critical.
Any other questions? Yes.
How do you select the standard stars? And another question, the difference between so much improvement in the performance when you had the coads, is that just increased signal to noise?
Yes, it's mostly we address it to that. It's just you have a higher signal to noise on average, and the star selection is quite simple actually. We only select stars with a probability in the Gaia catalog to be more than 90% a stellar object as a spectrum, and also the fit procedure is of multiple iterations. So every time we do some sigma clipping to just remove those that are outliers in the first iterations. We do 2-3 iterations in total, and then we get to a stable solution.
Any online questions? Okay, I'll take my prerogative as chair to ask a question as well. Have you also tried independently this with a smaller number of like high quality standards like the Landolt stars?
Yes, I tried I checked like a posteriori with the Landolt stars, the stability and is pretty high, and also I checked on some of the CalSpec stars, and also since now we have like a few months of operations, also checking the long-term stability of this. It's actually pretty good what we are seeing.
Okay, thank you. Any further questions? Oh,
Don't ask.
okay.
But now.
All right. There's always the coffee break. Okay. So let's thank Simone again. And our next speaker is Alain Smith. Hopefully I got close to the right answer there. And he'll be talking about towards a blind telluric correction.
Thank you. Good afternoon, everybody. I'd like to share with you some recent development on line correction. So this is a work that I've done a lot with Elias Sidariati. Florian Gerber has been very instrumental in bringing a radiometer and the first installation and then working at Paranal. Thomas Rose from the manufacturer of the radiometer has been also very valuable in bringing a number of features just suited for us, while John Pritchard, Plato, are really dealing with trying to make the tool very much as possible user-friendly. So this is the general structure of the talk. I will try to introduce what model fit is. Then I'll go to the next step, basically recent development towards blind telluric line correction. Major part regarding the importance of these FLUX calibrations, and conclude the presentation. So let's go through model fit. So this is a small part of the transmission of the atmosphere as seen just from the molecules. No relay scattering, no extinction here. And one can see, let's say in the optical, we have mainly water vapor, we have oxygen, we have ozone. As we go in the infrared, we have other molecules, CO2, methane, and then if we go even further away, up to 30 microns, we start to have quite a number of other molecules with more or less important contribution. So the standard method that is used to be done a number of years ago was, well, you observe a telluric standard star, that is a star typically of a B type, or if you're interested in features that are close to hydrogen line, you observe a solar type star. You observe it as close as possible in air mass, because all these absorption lines, some are on the, let's say, linear part of the curve of growth, others are not. You want to observe them goes in time because the atmosphere is changing, the amount of water vapor in the atmosphere is changing all the time. And then you divide the science spectrum by the telluric stars, and hopefully there are some tools that allow to take into account small differences. But of course, this costs observing time. You either spend your time observing your science or spend your time observing your calibrators. So let's try to bring this and try to do only science and trying to avoid to do any calibration. Oh, sorry. Okay, yeah, sorry. That of course, sometimes you don't have possibility to observe your telluric star because you have technical problems, or because the wind change direction is too strong and the dome is too close, or maybe you are taking data coming from the archive and the science goal of the proposer is not the one that has an archive research. So the best would be, can we do telluric transmissions with a static spectrum? But this is only possible if one knows a number of things like formation of the atmospheric lines, the parameters of all the molecules, the abundances of each molecules in the different atmospheric layer, the physical characteristics for each atmospheric layer, and also some instrumental features like the line spread function, maybe also the wavelength functions, which may not be ideal. So model fit is basically a driver to a radiative transfer code used by meteorologists. One of them is LBL-RTM, is the one that has been chosen. The parameters for the molecular lines is basically coming from ITRAN database through AER. The abundance of each molecule is coming from a standard atmosphere. Actually, it's not the standard atmosphere. There are many standard atmosphere. It's the one close to the equator. And what MoleFit does is, for each of the molecules that we consider, fit basically a constant factor for the abundance on each layer. For the physical characteristics of the atmosphere, the temperature and the pressure, we rely on GDAS profiles, that is, profiles that are provided by the astronomical organizations like NRO or the European Center of Medium Range Weather Forecast. For the line spread function, MoleFit includes a number of analytical functions like the Gaussian, Lorentz, or Bots, but there's the possibility with a user-provided line spread function. So in addition to this, MoleFit allows to correct for small mismatch in the wavelength calibration using the telluric lines themselves. And in order to be able to do all this, you also need to be able to fit the continuum. So why is it important to have the temperature and the pressure and the abundance of the different molecule? Here on the oh, sorry, I lost the pointer. Sorry. So here on the left, you have the abundance profile for the amount of water vapor, and you see how it changes as we go from close to the observatory to the upper side of the atmosphere. The two graphs the two lines that you see correspond to the same total amount of water vapor. The red one, the dashed red one, is has a maximum close to the observatory, but then decreases, while the black one has basically zero at the level of the observatory as a maximum, which is a bit higher than the other one starting at 2 or 3 kilometers. Now, when you try to see the transmission from these, you realize that the shape of the lines is different. If you look at the temperature, well, these are simulated spectra. When we divide the transmission spectrum with the ground-based temperature from 11 or 12 degrees for the top one, and between 2 and 12 degrees for the second one. And you see that when we divide the simulated spectra, we start to see features. So it's important to have all these parameters right. So how does MoleFit work? Well, basically, you don't need to fit the whole spectrum. You don't want to do that because you don't have calibrators. You try to do this on the science spectrum itself. You select small regions of the spectrum where you have lines produced by the different molecules that you are interested in, and you just try to get the best fit. So you are going to fit, in this case, the amount of water vapor, going to fit the parameters of the wavelength calibration and the continuum. Here, this inclusion region, the region that has been used for the fit, is shaded in yellow. And then in the second part of the tool, the second piece of software, so MoleFit Caltrans, you use the parameters that you found with your model, and you apply it to the whole spectral range of your spectrum. And you see this, so the original spectrum is in black, the corrected one is in red. So looks pretty good. Actually, this has been very much appreciated by all the astronomers studying the atmosphere of exoplanets, because it allows them to go and see very, very fine features. So this is a spectrum of a star called HD 197-733b, and here Romain Allard and the people from Geneva were looking for water vapor in the atmosphere of this exoplanet. So they were looking at faint features close to the telluric lines, which are marked here in green. So there are about 40 spectra actually plotted here. All these telluric features that are shown here have a range of air mass, which is color-coded with the scale there on the right. So just to see them better, if you subtract the average of the spectrum, you can see here very well. Now you apply to model fit, and this is what you get here on the left. Basically, the lines have basically disappeared, and if you subtract the mean, you see that you're basically in the noise. So this brings the conclusion from Allard et al. That basically the 1 sigma precision of 20 parts per million on the transmission spectrum demonstrate that space-like sensitivity can be achieved from the ground, even for molecule that is a strong telluric absorber. So no, saying basically that ARPS is basically doing on the same as it was flying above the atmosphere. So can we do better? Well, we can get the amount of water vapor from a radiometer. We can also, the radiometer can also provide not only the total problem density, but also the profile. We can get molecules by observing regularly telluric stars during twilight. And therefore, if the wavelength calibration is good, if you know your line spread function, and of course true if you are dealing with just a photometric correction, you would be able to get a transmission spectrum of the atmosphere or at any time and any direction in the sky. So this is done thanks to radiometers for the water vapor. This is the platform of the VLT. We have now 3 radiometers. First one, 14 years old, is the one. We bought another one 5 years ago, and then the NIST stars has already bought there, which will be transported in a few months to the final location. This is the kind of information that we get. We get the temperature profile, and we get the humidity profile. So all the amount of water vapor changes with altitude. And then we apply it from the temperature with water vapor. We can get also the pressure profile. We can compare it with coming from GDAS, and then we apply it. And this is the kind of correction. So here I didn't fit. It's a bit more complicated, but I will just limit to the case where I didn't fit the amount of water vapor. I just found that it was very much the same as if it fitted the water vapor. I can spend a bit more time later if you want. But this is the whole part of a UV spectrum where this previous extract part shorted part was shown. This is the whole spectral range of the upper red chip of UVs. You see how well it has been corrected. We have some features here at about 0.94 micron, which are probably caused by a problem in the sky subtraction in the UVs data reduction itself, just 1% level. Then this gray area has been expanded in this middle graph, and you see how well it goes. I wanted to try to quantify how good it is. So the standard deviation of the spectrum in the blue area here, and I get the selected area 0.019. I compare with the standard deviation of all the points in the corrected spectrum, and I get 0.018. And the ratio is between the two is 0.096. So actually the part that I had selected were a bit worse than the whole spectrum. I can compare this with over many tens of spectra. We made a lot of graphs here. So basically, when we are at amount of water vapor below 2.4 millimeter, which is the median for paranal, we are basically able to correct the amount, the telluric lines coming from water vapor very, very well. And as the amount of water vapor increases, then also the risk that it changes, the total column density of water vapor changes also increases. It's also much more dependent on the area in the sky when you're looking at. All this is just based on one single set of measurements on the radiometer. For the other molecules, well, we can go and, for example, look at the amount of CO2 in the atmosphere. So here are two fitting of the CO2 band, and from there we can get the evolution of CO2 over paranal, can confirm that the amount of CO2 increases. Unfortunately, over the last 10 years, we start to see some features that are related to probably wind coming from the Amazon during the altiplanic winter. Do the same for methane. And let's come to the last part of the talk, the importance for FLUX calibration. This is best illustrated with work that has been done by people looking for exoplanets. So we have speculoos, which is looking for planets around eclipsing ultra-cool stars, which, if you don't know, also speculoos is also very nice cookies. TRAPPIST, speculoos is a successor to TRAPPIST, and TRAPPIST are very, very good Belgian beer. So if you go to Belgium, enjoy. And I'm going to run a bit short of time, but just to illustrate, if they're looking for ultra-cool planets close to ultra-cool stars, then the R band, R and Z prim and I plus Z spectra are going to be very much affected by the amount of water vapor. This is how it goes with the temperature, the effective temperature of the stars. You see a very strong impact. And if they apply it, the correction that they can get from the expected amount of water vapor with what they get by comparing two stars of different temperature, you see here that this model is working very well and with the sub-milli magnitude level. So this is, I will leave it with my conclusions and go for questions.
Questions? Yes.
Yes, so thank you for this very exciting talk. So I was wondering, what about the hydroxyl lines that contribute quite significantly after 0.7 microns, and they're very variable? What are the cutting edge methods to getting rid of those for faint sources?
Okay, so you're talking for the OH lines, right?
Yes.
But this is more in emission, more than in transmission. Yes. It's a different problem. We're also working on that part. We have at Paranal, we have a set of, let's say, of instruments that are looking into this, and we are trying to find a way that we can use this kind of information to maybe predict what these wedge lines would be. But it's a completely different matter. It's in emission. While here,
can you say more about that?
Let's talk maybe afterwards, because yeah.
We do have a discussion session coming up where we're going to come back to ground-based versus space-based. So,
yes.
In the case when you don't have the radiometer data for the water vapor, you fit the actual water abundance as a function of height. What algorithm do you use for doing that? So, do you have any constraints on the profile that can be?
Well, if I don't have the data coming from the radiometer, I assume basically the kind of profile that the GDAS would give us. The GDAS is basically coming from world model of trying to actually, what the meteorologist says is reanalyzes data set. When they we run the model on observed quantities, and they do that for the whole world. So that's, I mean, the GDAS profile can be provided for all observatories. And so the problem for Paranal is that I don't have the graph here, but this GDAS profile is not very accurate for the Paranal location. And one of the problems is that we don't have enough weather stations nearby to actually fix the model. And that's why also the kind of information that we are going to get from the campaign, and maybe adding the number of weather stations close to Paranal to increase the probability that we can get the right weather forecast is important. But being in a desertic area where you don't have weather stations, be in a location when you have a lot of mountains that can bring a lot of differences, a lot of effects is actually make the GNAS profile not very accurate for things that are close to the atmosphere, and that's close to the surface. And that's why even the radiometer is important, because water vapor is basically located in the first few 100 meters.
Great. One last quick question.
So can you get, so this will correct for, in general for telluric lines. Can you also get, it's a higher order effect, but off of the surface of aerosols. Now aerosols are different business, but the surface of aerosols, there's no, you can, potentially get, adsorption of these species onto the surface of aerosols and perhaps get a little bit of telluric lines from the aerosols. Is that?
I would expect the aerosols to be causing more continuous absorption.
Okay, I mean, in general, that's true. But I wonder if you can also get little bits of line.
And I would expect this to be affecting more maybe the mid-infrared, the thermal infrared.
Yeah.
And yeah, it's another subject.
Great. Thank you so much. Let's thank Ellen again. Next, we have Joseph Moore talking about a homogeneously flux calibrated external ground-based data set for the Euclid mission.
Sorry, that's one.
See if I can find my talk. I noticed that mine was also missing. Oh, let's put on the desktop. Okay, thanks to the organizers for the opportunity to participate. Today I want to tell you a little bit about what we're doing with the ground-based data that are needed for the Euclid mission. This is a project that I've been working on with, as you can read, Koshi George, Tomas Vasalo, Igor Frumchenko at LMU on behalf of the Euclid mission. Okay, so the sort of design mantra for Euclid was do from space only what must be done from space. And so, as you heard from Misha, there's a Viz instrument on Euclid that is delivering optical images, 1.15 arcsecond image quality over a large field of view. There is a near-infrared instrument, NISP, that delivers deep Y, J, and H 0.45 arcsecond images over the same field of view. That's the space component. And down here, you can see, if I can get this, maybe I'll try using this. You can see the band passes of these, of Viz here and near IR. And in addition, then you see the ground-based data here, GRIZ in general, but we have also some U-band data. So it's this ground-based external data, EXT, I'll refer to it at different times, that is needed to provide SED constraints on the galaxy, so the photoz's for the weak cleansing experiment, and also because of this broad Viz band, it's important to know the color of an object to predict the PSF that Viz would have when you're trying to extract the shear. So we have to, given those science needs, we need to understand the fluxes at better than about 1% over the full 14,000 square degrees of the survey, half of which is in the north and half of which is in the south, in disconnected parts of the sky. There's also a color requirement, which has to do with this color-dependent PSF, which is 0.5% stability, not over the whole survey, but over the Viz field of view, so this point, 3/4 square degree image. So if we can achieve these things, then we can do the cutting-edge stage 4 cosmology. The external data set is very heterogeneous. So in the north, and here you have a map of the sky, in this blue region, These 4 patches correspond to what we call the Euclid region of interest. These are extragalactic sky regions that avoid obviously the galactic plane, but also the ecliptic plane because of the zodiacal light there. Up in the northern region, we have a survey which we call unions, which is a combination of 4 different surveys. HSC surveys, a WIGS G-band and a WISHES Z-band, sequence from Megacam, CFHT, R, and a little bit of U-band data, and then there's Pan-STARRS I-band. In the south, this region of the sky, we have the dark energy survey, just GRIZ, no U. And of course, Reuben is coming and will survey this entire region south of plus 15 declination. In addition, you can see on this map some locations. There are 3 different deep fields corresponding to about 50 square degrees of sky. We have, and also some auxiliary fields where there's lots of spectroscopic data that we can use to characterize or validate our photoses. And they're covered by HSC, a variety of bands. Unfortunately, HSC has had 2 R-band filters and 2 I-band filters. DS, of course, and unions, and then eventually Reuben will cover these southern fields. So homogeneously calibrating this heterogeneous data set that covers the whole sky is a challenge. And so we plan to leverage Gaia. And here's just the survey plan. You can see that Euclid basically surveys from the south ecliptic pole moving towards the ecliptic equator and the north ecliptic pole moving towards the equator over time. Okay, so 2 contextual slides. First, the Euclid photometry process. How does Euclid do this photometry? And then a little bit about how you might use Gaia to calibrate in the next slide. This, first of all, the Euclid photometry is extracted from the COAD images. So we have the VIS images, the 3 near-IR images, and then we have the external ground-based data, and they're all built into COADs. The images on the external side that we feed into those COADs are CCD-based images. They're detrended, astrometrically calibrated, they're given an initial photometric calibration, and this happens in different places. So the unions data are processed in Japan, Hawaii, and Canada by the survey leads. The DS data are processed at LMU by my team, starting from the public raw DCAM exposures. And the HSC deep and auxiliary data are processed also in Japan and Hawaii, depending on the different teams. All of these data, these heterogeneous data, are then Euclidized. In a sense, what we mean by that is that they're brought into a common data format, which we call a single frame, CEF. And this CEF contains the image, contains the catalog, contains a position variable PSF model, and an XML descriptor. And then what I'm going to talk about the rest of this is all of these CEFs are recalibrated photometrically in a process that leverages the Gaia data set, the Gaia spectra. Okay, and then after that process, which I'm about to describe in more detail, the CEFs are built into the COAD images, as mentioned before, and PSF models are calculated for every single object. A detection is then carried out on VIS and separately, and then the photometry is measured currently with either a VIS template, called a program called TPHOT, or aperture photometry, a program called APHOT. And in the TPHOT case, the PSF models in the external data, for example, or the near-IR data are used to transport the VIS template, the surface brightness distribution of the galaxy detected in VIS, to the near-infrared and X data, and then extract a kind of weighted color. The APHOT photometry, the PSF models, are used to basically homogenize the seeing, degrade everything to the worst seeing, and then measure the flux or colors within some chosen aperture. Okay, so that's Euclid photometry process. What about Gaia? So there are 2 basic ways, there may be more, but 2 basic ways to use the Gaia data set to do photometric calibration of ground-based data in this particular case. One is to build a statistical transformation expressing the X band, like this could be G band, in terms of the Gaia G photometry, plus some function of color. And for color, we use the BP and RP Gaia photometry. And over here on the right, you can see these transformation functions. This is the distribution of stars for G, R, I, and Z band. And this is the photometry minus the Gaia G. And you can see as function of color, because the stars are well behaved, there's a stellar sequence, there's a very nice transformation function, which we just fit a spline to. And the scatter here, you can't tell because of the dynamic range, but in this color range, it's about 1%. So for a single star, single Gaia star, you could calibrate an image at the 1% accuracy already. So you know you're going to be able to, well, you would hope you'd be able to do better. So an important concern is that this transformation of function approach is only as good as the stellar locus is constant. So you have to worry about galactic extinction or different populations of stars. The second approach, which is more stable, is to use synthetic magnitudes from Gaia spectra. So you take the band passes, S of lambda here, from each of the X survey bands, and you can basically use the Gaia calibrated spectra to predict or calculate the magnitudes, the synthetic magnitudes. Okay, so that's no mystery for this. For X calibration, then we have adopted these synthetic magnitudes, but we show in some of the slides some transfunction magnitudes as well. So aside from the wonderful Gaia papers that suggest that the Gaia photometry is calibrated at the 2 millimag level, why do we have some confidence that this might work? Well, over here, you can see the difference between the transformation function predicted I-band in DES versus the DS-DR2 I-band magnitude as a function of position over the survey. And down below, and you can see the range of offsets within 0.23 square degree pixels, so what Koshi chose to do this particular figure. You can see the distribution of offsets here, and the width of that distribution is 2.7 millimags. And what is this DSDR2 calibration? Well, that's the beautiful forward global modeling calibration technique of Eli Rykhoff and David Burke and others within the DS collaboration. And so you can see from just that simple transformation function, you can get to within, you can get a photometric calibration across 5,000 square degrees that agrees with Eli's calibration at with a scatter of about 2.7 millimags. And here they are. I'm only showing you the I-band image. The others look the same. But you can see that the differences, we're able to recover, in some sense, a calibration that's in good agreement with you know, the best ground-based calibration of a large survey that's been done so far, Eli's. So that gave us some confidence that this might actually work. We've also now done this also in the north with the unions calibration. And you know, we can create similar figures. The performance of that pan-stars-based calibration is not nearly, is not as good as the DS calibration. But anyway, there's no reason to believe that we can't play the same game in the north that we can play in the south. If we could use synthetic magnitudes, we should do better because we wouldn't have. We think that these issues where there are larger deviations have to do with extinction, or Eli said yesterday, maybe some blue stars over in this region. I'm not sure. Okay, so how do we do this calibration flow? Now, if I've convinced you that this is a reasonable thing to do, well, we process this guy tile by tile. So here's the Euclid year 1 survey region, and here's DS divided into a bunch of tiles. And since we have the Gaia calibration over the whole sky, we don't have to do a global calibration of the entire data set at once. We can do piece by piece using part of Gaia. So that's what we do, tile by tile. We try to stay ahead of the survey so that whenever the VIS and near-IR data come down, that the X data are available. So the Gaia synthetic photometry is calculated for all the X bands, DS, HSC, and then is applied as standards for the photometric calibration. And currently, we're assuming a single passband for each of the X bands. We're not mapping the passband variations across the field. We'll do that next. So Gaia-based photometric calibration, this is straightforward. To clarify, for each of these sky tiles that we're calibrating, here's one for DChem-I, we basically grab all of the CEFs. We only need the catalogs in the XML. The catalogs contain PSF fitting stellar photometry, and that's what we use to calibrate to that Gaia to that stellar photometry. And the Gaia spectral-based photometric standards, or synthetic magnitudes, are also inputs. And we use corrected synthetic magnitudes down to 17.5 mag. I can have some extra slides to talk about that if someone's interested. The calibration method then is that this super tile has too much data, or sky tile, to process in a single job. And so we divide it up in some overlapping, in some subregions, where each region overlaps the neighboring subregion to ensure no discontinuities as we move from, subregion 15 to 16 or something, if you understand what I mean. We build up a matrix of constraints for all the Ceph 0 points. We assign a single degree of freedom to each of these Cephs, each CCD image. We call that the 0 point. We put the direct constraints from any Gaia spectra, there are about 50 on average that lie at high galactic latitude on the DS chip, which is 10 by 20 arc minutes. And we also have relative constraints from overlapping Cephs. So we can use the stellar photometry and overlapping Cephs to not tell us what the 0 point is, but what the difference in the 0 point between Ceph I and Ceph I plus 1 would be. Then we simply invert that matrix. We get an inverse variance weighted solution and look at validation metrics and see if there's any reason that our process has failed and move on. 1 minute. Okay. So we are able to get, there's a lot of information in this, so we're able to calibrate the 0 points quite accurately to like a millimag. Of course, that doesn't include the Gaia systematics, which are 2+ mags. So this means we can tie our photometric system tightly to Gaia. Here's some example photometry for DS, and I have a similar plot for unions. What's interesting here is the scatter that we're seeing, which is telling us something about our photometry, how good the detrending is. You can see a little trend here in R band, which is a concern. Happy to talk about that. And here's similar for unions. So we're able, just as a demonstration that this is working. Accuracy considerations, if I may. So we try to use 1 to 5 square degree calibration patches to help us reduce the impact of Gaia striping. What is Gaia striping? So you can see these features here on the map. They're at a low absolute value, but they're driving some of the systematics, the systematic floor in Gaia. And you can see that they're not so broad, and so if we use big patches, we might hope that we can calibrate out some of those problems. In addition, you can, because we're using, here's a difference between the synthetic magnitudes and the transformation function magnitudes in Z-band, and you can see these features. That's clearly galactic extinction coming in. So we're able to avoid all that by just using synthetic magnitudes. And then I think our next plan is to basically use, to map the focal plane variations in the pass bands. Here's I band and D cam. You can see there's a center to edge, well-known center to edge effect that just pops right out with this Gaia calibration information. And summary then is that the external data are tightly calibrated to the Gaia photometric system, or that's our plan. We're currently doing that. And it looks like we can easily reach our 1% photometric stability, but we haven't actually demonstrated that we're reaching this color stability. That's still an open question. Current calibration assumes a single band pass per X band, assumes that the atmosphere is gray, and extracts a single 0 point. Next step is to map out the bandpass variations for each of the X cameras. That will be quite a task, and improve the flatness of the Cephs using our flat correction. We've already done that in the case of DES, but not for the union survey. And so the bottom line then is that Gaia offers, I think, better than percent level photometry to ground-based optical data, basically because there are 200 million spectral calibrators spread all over the sky that you can use to do your calibration. So thank you for your attention. Sorry.
Time for one quick question.
Do you think that some of the color instability has to do with like changing 0 points for ground observatories? Like U band changes faster than R band?
I don't know. I don't think so. I think that the main problem that we have with this approach, there are two problems. One is that the quality of the Gaia data will continue to improve. It's already good enough for Euclid's purposes. And the band passes that were given from the different survey teams are as good as they can get, but there are errors there that will influence our calibration. I think those are our two main concerns.
Okay, one online question.
Yeah, quick question from Bob Buchheim. Is there a bright limit to using the method?
Yeah, there's kind of a faint limit that the Gaia standards only go down to about 17.5. Bright limit would be the saturation in your ground-based survey. So in the case of DS, it's 14 to 17.5 we can use, there's no problem. At HSC saturates quite to 16th magnitudes, there's a narrow limit there. And CFIS-R is also 16.5, something like that. That's a concern for sure.
Okay, let's thank Joe again. Next up, we have Brian Kloppenborg talking about methods and issues with flux calibration methods employed by student researchers and amateur astronomers, I assume. Got cut off in the...
Yeah, I think we heard there was a competition for the longest title. I might have won that because I think you hit the limit. I do. Although I did clip my title a little bit, so I might be in second place now. So, thank you very much for the opportunity to speak with you today. So just to quickly summarize what I'm going to be talking about, the bottom line up front is that in terms of photometry, most students and amateur astronomers practice differential photometry. And as we heard from Chris on Tuesday, professional instruments can get you better than 1%. It turns out that consumer grade devices can also get you better than 1% fairly easily as well. However, there's a whole bunch of heterogeneity in terms of how people acquire their data, calibrate it, their filters, et cetera, that really reduces the aggregate performance of student and amateur photometry kind of to about the 5 to 10% level, or in some cases a little bit worse, which I'll show you a couple ugly examples in a few minutes. In terms of spectroscopy, most of the time students and amateurs, they'll end up doing wavelength calibration and instrumental response correction, but that's kind of where it stops. Unfortunately, most of the databases that they contribute their data to don't actually require them to do flux calibration. And unsurprisingly, the software that they're using to reduce their data also doesn't support it, with one exception. But we do have a few spectroscopic observers that actually do calibrate their flux, and they can produce results that are consistent with each other to within 5%. Now, before I talk about these items in detail, in case you've never heard of the AAVSO before, I'd just like to mention that we're a 113-year-old nonprofit organization based here in the United States. And what we do is we provide students and amateur astronomers an opportunity to make a direct contribution to science. Now, the way that we do that as an organization is we provide education and training, observational programs, as well as data curation and data dissemination to get their data into your hands. And classically speaking, we're known for doing variable stars. However, we really have 4 key focus areas, which include stellar photometry, stellar spectroscopy, exoplanet photometry, and sunspot. Now, we are a really small organization. We only have 6 full-time employees, and our budget is $1 million per year, but we really have an outsized impact. Our data, products, and services that are generated by staff, former employees, as well as our amateur astronomers and students that contribute to our databases are cited in over 250 publications, 250 peer-reviewed publications per year, which is really quite extraordinary considering that's all done on $1 million a year budget. But I'm here to talk about photometry. So in terms of the techniques used by student and amateurs, many of you all probably learned these. Really 2 of them that are used. One of them is in-frame differential photometry, which is usually done on fairly narrow fields of view. So we're talking something that's somewhere between like 1/4 degree and maybe 1 degree, kind of at the largest. In these cases, people usually calibrate their data against, it's a relative photometry, I think would be the terms that you would be using here. They usually calibrate their data against maybe 1 or 2 stars and then check against another star, or they'll use some kind of an ensemble with like 20 or so stars to create their reference frame. Usually these types of data, since the field of view is so narrow, there's not a whole lot of impacts from air mass, and so usually they're just going to do 0-point and color corrections. However, we also have a few observers who are still using photoelectric devices, 1p21 photomultipliers or photodiodes. Those people are hopping between different regions of the sky, and so they're doing what we call all-sky differential photometry. And so these are with fields of view that are kind of 5 degrees or larger, or they're using single pixel detectors. They traditionally calibrate things only against 1 to 2 stars at any given moment in time, but they've gone through and figured out the other calibration coefficients that they might need. And they usually end up doing 0-point color and extinction correction. Now, one trend that we've noticed that's pretty interesting is that the people that calibrate their data against a smaller number of stars have really tight errors. But when you start to extend that out into these ensembles, the uncertainties grow very quickly, and they don't go down as kind of like a 1 over the square root of n like you would expect from averaging. And so we think there's actually a lot of problems within these photometric catalogs that we use as our reference frame. Now, when these techniques are applied well, the light curves look absolutely wonderful. This is a great example of what Betelgeuse looks like from amateur and student data. Here, there are 216 different data points acquired by 11 different observers, and most people submitted fewer than 10 observations. And so you would be really hard-pressed to identify any kind of systematic offset between the individual observers, with the exception of those points that are really clearly outliers. Now, this is kind of, after this point, this is where things start to go bad. So when we did a meta-analysis of our catalog specifically for this workshop, and ignoring visual observers for a moment, by the way, about 60% of the people that contribute to our database are out there observing with their eye. It's actually a really fun thing to do if you've never tried it before, so give it a shot. But in terms of the people that are using digital detectors, folks with CCD and CMOS sensors, they're usually quoting internal uncertainties. So this is just the deviation of the data points that they've acquired, kind of on the order of 10 to 50 millimagnitudes, whereas individuals that are using photoelectric devices, so these will be your 1p21 photomultipliers and other types of photodiodes, they have internal uncertainties between 5 to 10 millimagnitudes. So if you pick an uncertainty and pick a magnitude, the folks that are using the photoelectric devices are doing better than 1% photometry, whereas the people that are doing CCD work are usually kind of on the order of 1%. Unfortunately, that's not. Unfortunately, things kind of get a little bit worse from here. So if you look at the devices that people are using, here's a couple of response curves for the 1p21 photomultiplier in green, CCD sensors in blue, CMOS sensors in red, and a typical photodiode that's shown there in yellow. You can see that the spectral responses of these different sensors are really quite different. And so you can usually minimize these things by using photometric filters, because then basically you just have a color term that you need to adjust for. But unfortunately, commercial photometric filters vary quite dramatically. So here I've shown a plot of Johnson's V on the left, Cousin's I in the middle, and the G and G prime Sloan filters on the right-hand side. The shaded region in the background is the reference filter implementation, and the lines that you see in the foreground are various commercial filters that are being sold on the market. Now, I'd like to pick on the one in the middle, Johnson's I, especially because I just bought one of these filters myself. It turns out that most filter manufacturers are still building their filters according to the 1965 Johnson specification, despite the fact that there was a paper in the 1990s which showed that the effective response curve for that photometric reference system, you need to factor in the instrument, which had a really strong cutoff around 900 nanometers. And so if you have one of these I-band filters, you could be emitting something like 2 to 2.25 times more light than what you actually should be. So the kind of takeaway on this one is that commercial Johnson-Cousins filters can vary somewhere between 10 to 75% of the standard, and Sloan filters can differ by 10 to 20%, depending on where you get them. Now, of course, as professional astronomers, like, we go out and buy tightly controlled filters, but amateur astronomers and students, they just go buy something that's available in your local astronomy store. Now, most people don't get into photometry using monochrome sensors. Instead, they come from the RGB world. And I think it's pretty easy to state that red, green, blue cameras, so these are like CMOS sensors with a Bayer array with colored pixels in front of them. These cameras are not standardized in any way. So in the left-hand side, I show a plot of the blue, green, and red transmission filters from front-side illuminated CMOS sensors. So these are kind of up to maybe about 2013, 2014 time period is when these were being made. And you can see that, by looking at the stacks of these filter curves, there seems to be pretty good agreement. However, There's actually a lot of deviation between them, especially when you go over to the red filter. And then I'd like to call your attention to the bottom right-hand corner of this plot. In black, I show what a traditional monochrome CMOS sensor would look like in terms of its response. Contrast that with two different green sensors from Sony. They're both Sony IMX lines, and you can see that not only is there a really large infrared leak, and that's because this is a backside illuminated sensor with a deeper photosite, so it's more sensitive to the infrared, and it turns out that the dye is actually transparent to the near infrared. But also, if you look at the green response, it's kind of there, around 550 nanometers. Green is not green. So we have a lot of problems to deal with. Now, AVSO, right, we've been around for 113 years, so we've really had to evolve as the field of photometry has evolved. And one thing that we've done is we've tried to adapt to the latest and greatest photometric reference frames that we can provide to our members. We provide folks with sky charts or star charts that show comparison star magnitudes. You can also grab the underlying data to those things as well. And what we have done is our catalogs, basically, if you span all the way from -2 at the brightest to +19 at the faintest, our brightest catalogs are from the General Catalog of Photometric Data, which was built back in the 1990s, with data going back until the 1980s. Then going a little bit fainter, we use Tycho 2, and there's a really interesting historical interplay between these two catalogs because they were actually assembled by the same group, but I won't go into that today. In the middle, kind of around 7 to 17th magnitude, we use the AVSO's own APAS survey, which is actually anchored to the Landolt photometric system, and you all probably know that Landolt had slightly different filters than the Johnson's filters, so he truly is a different photometric system, kind of at that 1% level. We also use the primed Sloan filters. And there's been a lot of discussion about pan-stars and Gaia kind of at the fainter end. But the typical photometric uncertainties quoted in these catalogs are kind of on the order of, let's say, 10 millimagnitudes to maybe 60 millimagnitudes. But as I mentioned before, the way that we construct our photometric reference frame is we go through these catalogs, we find the non-variable stars, and we tell people to use these photometric references so you don't accidentally impart the variable signature of one star onto the light curve of another star. So that means that we've already vetted these things to the greatest extent that we can, but yet when you take and you start to aggregate them, beyond 2 to 3 stars, we start to see the uncertainties growing, whereas in reality, the more background stars that you have to nail down the reference frame, the uncertainties should shrink. And so there is some problems in all of these catalogs, including our very own. So all of these issues combine to create a wide variety of different problems. And I've shown a couple of examples here on this plot, and I'll call your attention to the bottom, where we have an individual that's observing in a tricolor blue filter, which is this top tracer here. Another observer observing in tricolor blue, as well as an observer down here observing in a Johnson-Cousins blue filter. And you can see that there's an offset of about 7/10 of a magnitude. If you look up at the green trace, which is Johnson-Cousins V, you look at that and you're like, oh, okay, that's not too bad, right? Well, if you blow it up and you look at things, there's a couple of different traces where you can pick out the individual observers, and the overall scatter is kind of about 1/10 of a magnitude, which means that single observers, although they can produce photometry that's better than 1%, in aggregate, all of these problems combine to make something that's really kind of at the 5 to 10% level. Now on to spectroscopy. Suffice it to say that amateur astronomers and students actually have access to a pretty wide variety of different spectroscopic instruments. The very first item on here, it's a grating that you put into a filter wheel. It's about $200 and it functions as a spectrometer. Down at the bottom, you have a Shelly Whoop shell, which is one of these call for price items. But I do know that people actually do go out and buy them, and it can deliver something that has a resolution of about 30,000. These are all very nice instruments. Most people pick something that's a few $1,000s and delivers a resolution of an R of maybe 2,000 to about 10,000. Unfortunately, the software that they use to reduce this data do a whole bunch of different things. You can see in terms of the wavelength calibration, they're using something between a second and maybe a fourth order polynomial, where they don't really discuss what they're doing. The IRF correction, it's usually some reference spectrum, and then you fit to the continuum, and that's work. But when it comes over to the column that we care about at this meeting, only one of those packages supports flux calibration, and it does that using synthetic photometry. So if you're observing a variable star, not only do you have to observe the variable star photometrically, but you also spectroscopically, but you also have to observe it photometrically to anchor your data back to some kind of a reference system. So it really is quite a mess. And I don't know if it's because of the software or it's because of the underlying databases here. You can see that none of the databases, again, including my very own with the AVSO, require flux calibration. So it is quite unfortunate. And lastly here, I just say that we could really use your help. So in terms of photometry, right, I could use some help investigating some of these intersystem calibration issues between the systems and also within the systems themselves. We're presently extending our APAS survey to go all the way up to second magnitude in the Sloan filters plus Johnson Cousins B and V. We could use help, reducing those data, doing an UberCal, or perhaps checking it against CalSpec. For Peter, I don't know where you went with the Landalt mission, but please laser telescopes that AVSO proper owns. We have a robotic worldwide telescope network. And in terms of spectroscopy, I'd really appreciate if anybody would come up during the break and tell me, what flux calibration method is actually reasonable for amateur astronomers to be able to do. And if you're a software developer, please try to add support to these commercial spectrographs to your packages, especially if you're on the Pipet team. I'd really like to see a slitless spectrograph added to the package. So with that, that's the end of my time.
Good. So I'm going to take my prerogative as chair to just say thank you for APAS, because I've used it many a time for fitting foot SEDs for white dwarfs, and it usually works pretty well.
Yeah.
So thank you.
We're happy it could be a service of the community.
Yeah. Yes.
Yes, actually, well, I would like to join in that. I also use APAS, and I think it has been very useful for me. So I also thank you for that. And in trying to return the favor, I have a paper published last year, which I think may be of use to you. So I reprocessed all the Gaia stars, basically about 90% of Gaia stars up to magnitude G17, and I calculated the photometric amplitudes of all of them based on the Gaia data itself. So if you want a database of stars that are non-variable, you done it in a uniform way with Gaia, you can take a look at that.
Yeah, that would be wonderful. We're actually planning on replacing our calibration star database in 2025 to solve some of the problems that I mentioned here. So I'll give you the card, and we can get in touch when I come up back that way.
Any other questions? Yes.
So I have a terminology question, because I'm wondering ultimately I'll tell you the reason I'm asking, but what is your definition for IRF? Because I think of instrument response function in a much more general way, and separating flux calibration from IRF to me doesn't make any sense. But what is your definition of IRF?
Yeah, so I think the answer is yes. That seems like a really dumb way to reply. Each one of these spectroscopic reduction packages approaches IRF differently. And so it seems like a very obvious answer, but they all have a slightly different way of doing it. So there's not a consistent way of defining what IRF is within the software that amateurs use. But usually what it does is they'll go and observe a standard star, and then they take the standard star, or they take their standard star measurement, divide it by the true standard star measurement, and that gives them a correction curve that is fit to the continuum points effectively. So it's a continuous spline interpolation of whatever that division ends up being. So what you end up getting for the calibrated spectra is it still has all the telluric lines in there, which are really useful for calibration, I might add, and it's not on any form of an absolute flux scale. So it's an intermediate data product that most professional pipelines wouldn't even write to a file, but it turns out to be the common way that amateurs and students submit their data.
Thanks, that helps.
Yeah.
Any online questions? Okay. Any further questions from the audience? If not, that concludes session 6A, and you all are free to get some coffee and snacks. Thank you, speakers. Good job.